When dealing with an emergency generator located separately from the main electrical room, the question of how to properly ground the system arises. If the main ground collector bus is in the main electrical room and a raceway exists between the generator and that bus, you can pull a grounding conductor back to the main ground collector bus. The system is considered a separately derived system due to the physical separation between the generator and the main electrical room, particularly if the neutral is not switched in the transfer switch. A separately derived system requires specific grounding considerations to ensure safety and proper operation. To establish a proper grounding system for the generator, follow these steps. Firstly, install a ground rod at the generator location. Secondly, connect the generator's neutral conductor to the ground rod. Thirdly, run a grounding conductor from the generator to the main ground collector bus. This grounding conductor is typically a bare copper wire. These steps collectively create a robust grounding system that ensures the generator is properly grounded and any ground fault current will reliably return to the source of the fault. It is crucial to understand the concept of a separately derived system. A separately derived system, by definition, is an electrical source that is not directly connected to the building's main electrical service. This separation necessitates that the system be grounded independently to ensure safety and prevent electrical hazards. Because the neutral is not switched, this means the generator's neutral is isolated from the main service neutral when the generator is operating. Therefore, it needs its own grounding system to provide a path for fault currents. The ground rod installed at the generator location serves as the initial grounding point for the generator's neutral. Connecting the generator's neutral conductor to this ground rod establishes a local ground reference. This is essential for stabilizing the neutral potential and providing a lower impedance path for fault currents to return to the source. The grounding conductor that runs from the generator to the main ground collector bus provides an additional path for fault currents. This connection helps to ensure that the generator's grounding system is integrated with the building's overall grounding system. This integration is important for maintaining equipotential bonding throughout the electrical system. Equipotential bonding minimizes voltage differences between conductive parts, reducing the risk of electric shock. By connecting the generator's grounding system to the main ground collector bus, you are essentially tying the generator's ground potential to the building's ground potential. This helps to ensure that all conductive surfaces in the building are at the same potential, regardless of whether they are connected to the generator or the main electrical service. In addition to these grounding requirements, it is also important to comply with all applicable electrical codes and standards. The National Electrical Code, often referred to as the NEC, provides detailed requirements for grounding separately derived systems. Consult the NEC to ensure that your grounding system meets all necessary requirements. Specifically, review Article 250 of the NEC, which covers grounding and bonding. This article provides comprehensive guidelines for grounding electrical systems, including separately derived systems. Pay close attention to the sections that address grounding electrode systems, grounding conductors, and bonding requirements. When selecting the appropriate size for the grounding conductor, refer to NEC Table 250.102 colon. This table provides guidance on sizing grounding conductors based on the size of the ungrounded conductors. Ensure that the grounding conductor is large enough to safely carry the maximum available fault current. The ground rod itself must also meet certain requirements. The NEC specifies the minimum size and depth for ground rods. Typically, a ground rod must be at least 8 feet long and must be driven into the ground so that at least 8 feet of its length is in contact with the soil. The ground rod must also be made of a conductive material, such as copper or galvanized steel. When installing the ground rod, select a location that is free from obstructions and that has good soil conductivity. Avoid areas that are rocky or sandy, as these types of soil may not provide adequate grounding. If possible, choose a location that is moist, as moist soil is more conductive than dry soil. The connection between the grounding conductor and the ground rod must be made using a listed and labeled connector. This connector must be suitable for direct burial and must be able to withstand the corrosive effects of the soil. Ensure that the connection is tight and secure to prevent it from loosening over time. In addition to the ground rod and grounding conductor, it is also important to bond all metal enclosures and equipment associated with the generator. This includes the generator frame, the transfer switch enclosure, and any metal conduit or raceways. Bonding these metal parts helps to ensure that they are all at the same potential, reducing the risk of electric shock. Bonding can be accomplished by using bonding jumpers or bonding screws. Bonding jumpers are short lengths of wire that are used to connect two or more metal parts together. Bonding screws are special screws that are designed to provide a low impedance connection between metal parts. When installing bonding jumpers or bonding screws, ensure that they are properly sized and that they are securely fastened. The bonding jumper or bonding screw must be large enough to carry the maximum available fault current. The connection must be tight and secure to prevent it from loosening over time. It is also important to inspect the grounding system periodically to ensure that it is functioning properly. Check the ground rod connection to make sure that it is tight and secure. Inspect the grounding conductor to make sure that it is not damaged or corroded. Test the grounding system using a ground resistance meter to verify that it is providing adequate grounding. If you find any problems with the grounding system, correct them immediately. A faulty grounding system can pose a serious safety hazard. If you are not qualified to repair the grounding system yourself, contact a qualified electrician. The proper grounding of a separately derived system, such as an emergency generator, is crucial for ensuring safety and preventing electrical hazards. By following these steps and complying with all applicable electrical codes and standards, you can create a robust grounding system that will protect people and equipment from electrical shock and damage. Moreover, consider the specific characteristics of the generator itself. The generator's manufacturer typically provides detailed instructions for grounding the unit. Adhere to these instructions carefully, as they may include specific recommendations for the type of grounding electrode to use, the size of the grounding conductor, and the location of the grounding connections. The transfer switch, which is used to switch between the main electrical service and the generator, also plays a critical role in the grounding system. If the transfer switch is a non-automatic type, it is particularly important to ensure that the neutral conductor is properly switched. In a separately derived system where the neutral is not switched, the generator's neutral must be grounded separately from the main service neutral. However, if the transfer switch is designed to switch the neutral, the grounding requirements may be different. In this case, the generator's neutral may be connected to the main service neutral when the generator is not operating. This can simplify the grounding system, but it is important to ensure that the transfer switch is properly rated and that it is installed correctly. Regardless of the type of transfer switch used, it is always a good idea to consult with a qualified electrician to ensure that the grounding system is properly designed and installed. An electrician can assess the specific characteristics of your electrical system and recommend the best grounding solution for your needs. In addition to the technical aspects of grounding, it is also important to consider the administrative and regulatory requirements. In many jurisdictions, electrical work must be performed by a licensed electrician and must be inspected by a qualified electrical inspector. Before starting any electrical work, check with your local authorities to determine the permitting and inspection requirements. Obtaining the necessary permits and inspections can help to ensure that the electrical work is performed safely and in compliance with all applicable codes and standards. This can protect you from liability in the event of an electrical accident or fire. Furthermore, keep accurate records of all electrical work performed in the generator and the grounding system. These records should include the date of the work, the name of the electrician who performed the work, a description of the work performed, and any test results. These records can be valuable for troubleshooting problems and for demonstrating compliance with regulatory requirements. Proper grounding is not a one-time task, it is an ongoing process. The grounding system should be inspected and tested periodically to ensure that it is functioning properly. Any problems that are identified should be corrected promptly. By taking these steps, you can help to ensure that your separately derived generator system is safe and reliable. Consider a scenario to illustrate these points. Imagine a hospital with an emergency generator located in a separate building from the main electrical room. The generator is designed to provide backup power in the event of a power outage. To ensure that the generator can safely and reliably provide power, it is essential to properly ground the system. In this scenario, the generator would be considered a separately derived system. The generator's neutral would need to be grounded separately from the main service neutral. This would involve installing a ground rod at the generator location, connecting the generator's neutral to the ground rod, and running a grounding conductor from the generator to the main ground collector bus. The hospital would also need to bond all metal enclosures and equipment associated with the generator, including the generator frame, the transfer switch enclosure, and any metal conduit or raceways. This would help to ensure that all conductive surfaces in the hospital are at the same potential, reducing the risk of electric shock. The hospital would also need to inspect and test the grounding system periodically to ensure that it is functioning properly. This would involve checking the ground rod connection, inspecting the grounding conductor, and testing the grounding system using a ground resistance meter. By following these steps, the hospital can ensure that its emergency generator is properly grounded and that it can safely and reliably provide backup power in the event of a power outage. This is critical for protecting patients and staff and for maintaining the hospital's essential services. In conclusion, grounding a separately derived system like an emergency generator requires careful attention to detail and adherence to applicable electrical codes and standards. By following the steps outlined above and consulting with a qualified electrician, you can create a robust grounding system that will protect people and equipment from electrical hazards. Remember the importance of installing a ground rod, connecting the neutral, running a grounding conductor, bonding metal parts, and regularly inspecting the system. Prioritize safety and compliance with the NEC for a reliable and secure electrical system.